Quando tiver alguém, fala, hein?
Ok. Ok.
Bom dia a todas e todos. Meu nome é Luiz Arthur, sou professor do programa de Engenharia de Sistemas e Computação, na linha de Computação e Sociedade, parte da comissão organizadora da Semana PESC. Semana PESC é um evento que a gente organiza já tem desde 2014. O objetivo é apresentar o programa, as suas iniciativas e temas interessantes de graduandos, né, e também comunidade externa da UFRJ. Então, nessa edição de 2025, a gente vai sempre começar às 11 horas aqui. A gente vai ter palestras de hoje, né, até quinta-feira, e com muitos temas, né? Peço que vocês vão no site do PESC, né, cos.ufrj.br, também no Instagram do PESC, que é coppe.sistemas, e confiram a programação. Mas um resumo, né, a gente vai ter um momento para apresentar pesquisas de jovens cientistas do nosso estado, né, uma categoria que a FAPERJ apoia, né. Vamos ter egressos do PESC, doutorandos do PESC, né, que já fecharam seu doutorado e que abriram empresas, startups, vão falar sobre esses projetos. Docentes do PESC premiados também, que vão falar aqui sobre suas pesquisas. E também um painel fechando, né, na quinta-feira sobre por que você deve fazer mestrado, doutorado no PESC. A gente está vendo que tem alunos de graduação aqui, né, então um convite para o pessoal ouvir um pouquinho mais. E a gente vai abrir com uma palestra internacional, e para apresentar essa palestra, eu vou chamar o professor Daniel Aton, também da comissão organizadora, né, somos eu, o professor Daniel e o professor Adriano. Então, Daniel, venha para a gente começar.
Obrigado, Luiz, pela apresentação e pela organização do evento, né? A Semana PESC, como o Luiz comentou, a gente já faz isso desde 2014, né? E é um evento que a gente tenta apresentar para os alunos da graduação o que a gente faz no PESC. Então, eu vou apresentar o Kostya, é a primeira vez dele no Brasil, ele não fala português, então eu vou trocar para inglês. So I'm going to change to English to present our distinguished speaker. So Kostya Avrachenkov is a researcher at INRIA in France, and INRIA is one of the well-known research institutes in France. Kostya got his PhD in 1999 in Australia, and then did a postdoc at INRIA and liked it so much. It's very nice in INRIA, in Sofia Antipolis, where he is. And he stayed there and did his career there. Kostya has worked on many different topics, performance evaluation on communication networks, and also on game theory, and also on network science, focusing on problems of clustering, network clustering, which is a topic of his talk today. So he has covered a wide range of topics. His background is in mathematics and control theory, so he's very well equipped to work on different problems. And Kostya and I know each other for a long time. We had a joint research project between Brazil and France, INRIA and UFRJ, and his research group and my research group in 2014, which lasted for about 5 years. And then after the pandemic, we didn't collaborate anymore, and we're trying to speak up the collaboration again this year. It's the first time he's coming to Brazil, so it's very nice to have you here. I hope you enjoy your time. He was in Porto Alegre 2 weeks ago, and now he's in Rio de Janeiro, saving the best for last before he returns to France this weekend. So welcome to our department, to the university. Looking forward to your talk. Thank you for being here.
Thank you very much, Daniel, for this very kind introduction. Indeed, I saved the best for my 3-week trip, and yeah, so far I think it was a good decision, right decision. So let's start with the technical talk. First of all, I would like to acknowledge that this talk is based on a series of works. And these are just some of my collaborators, and I think I even didn't mention all of them because this talk is aggregation of a few results about graph clustering. So I worked with a group from University of Aalto in Finland, the group of Professor Leskela. So in particular, Luz is a PhD student of Lasse Leskela, also in Aalto. Maximilian Trefton is my former PhD student, and now postdoc in EPFL. Vinay Kumar is my former postdoc, and now assistant professor in IIT Bombay. And I mentioned also some recent collaboration work with Lucas Filipe and Daniel Benache from this university. So, graph cluster. Let me start with some examples of applications. One very interesting example is clustering of connectome. Connectome is in fact a map of neurons and neuron connections in the brain. And the task is to understand which regions in the brain help to organize certain human activity. Another interesting application in sociology, so you have, say, a series of calls or interactions between persons. So suppose this represents a call on Monday between Bob and Cecile, and this corresponds a call on Tuesday between Alice and Cecile, and maybe on Thursday the three, Alice, Bob, and Cecile, have a Zoom meeting, online Zoom meeting, and this represents by this hyper age. So given this data in time, we would like to understand what is the social structure of a group of people. Just to mention a few applications, but I will be speaking about these applications in more detail during my talk. So, first of all, a word of caution. There's no panacea, as often the case, for the graph clustering problem. So there is no method which works uniformly well for all type of graphs. So you need to make some assumptions about the graph structure and then to take appropriate methods for clustering that type of graphs. So let us start maybe with the simplest graph model, random graph model, and we start with the first random graph model, which was developed by Erdős and Renyi in 1950s. So what is this model? We have a set of nodes. We take uniformly a pair of nodes, and we create an edge between this pair of nodes with probability, say, some constant a times log n divided by n. And we get something like this. So an important fact to know is that if the constant a is strictly greater than 1, then the graph with high probability will be connected. So in fact, you see, it's not right, it's not that for sure it will be connected. It will be connected with high probability and in the limit, but n is large. So here I have 40 nodes, and another example, of course, you can have disconnected node in the finite case. So that's a building block for our clustering model. So what would be our cluster model with the cluster structure? It is based on Erdős-Renyi graph, but now we have two sets of nodes. So suppose we have a set of nodes with blue labels and a set of nodes with red labels. And now we have two connection probabilities. So with probability P as before, and this probability has the form as before, we connect nodes inside each group, inside each set. Right? So between two nodes chosen uniformly at random, say two nodes of red color, we make a link with probability P of n. With the same probability, we also make a connection between two nodes chosen from the blue class. And then with probability Q of n, which differs by the constant B, we make a connection across classes, across groups. And typically we're interested in the case where the constant A is strictly bigger than constant B. So that's our model. Yes, please.
If we use two groups of nodes, why don't we use like n divided by 2? When we
it's just a matter of constant, right? So it can be absorbed here. So it's not important.
Oh.
Okay, so we have two groups of nodes. But now let us erase labels, right? So if we erase labels, but kind of keep our knowledge of the labels attached to the figure, we still see two clusters, right? But now let us permute also the nodes on the figure, right? So we don't, the cluster kind of disappears, at least it's not obvious anymore, right? What would be the clustering structure? And our task is, given this mess, to recover the clustering structure. So, formally speaking, we are given a graph, and we need to produce a partition of this graph, which corresponds to the original, like blue and red set. Yeah, so this is actually what I said already. And of course, you know, it doesn't matter for us if we recover, more or less correctly first cluster in blue and the second cluster in red, or the other way around, right? If we cover the first cluster in red or the second cluster in blue. So what matters for us is the partition, not the color with which we cover the sets. So therefore we aim to achieve exact recovery. And what is exact recovery? It's producing some estimate sigma hat such that it's either correspond to the plus with the original coloring or to the opposite coloring. So as we agreed, it doesn't matter. So this probability will need to go to 1 when the size of the class or size of the graph goes to infinity. And so basically, it says that in the limit, we will not have any mistake with probability 1. Okay, so already, actually, yes, it's 10 years back, two groups of researchers, in fact, more or less independently, obtained a very fundamental result in this domain. And the result is like this. So there's a phase transition. So if square root of A minus square root of B squared is strictly greater than 2, the clusters can be exactly recovered in the SBM model with two clusters with probability convergent to 1. And if the opposite condition with the strict inequality holds, no algorithm can exactly recover the clusters with probability convergent to 1. So it's kind of phase transition result. And just a quick note that this condition, which is in the theorem, can be rewritten in the following form. So here actually it's related to equation 2, right? So here we can divide A and B by 2. So this condition says that we need a little bit more than the total connectivity of the graph. So without plus square root of AB, it would be just a connectivity condition for the whole graph. So this condition says that to find correct cluster structure, we need a little bit more than connectivity. Okay, so how do we do this? We can do actually with some simple algorithm. And the first algorithm is based on spectral technique. So let us again kind of unwind our clustered graph. Suppose we kind of know that the first set is, say, from 1 to n divided by 2, roughly, and the second set from n divided by 2 to n, right? So if we arrange nodes in this order, and we look at the shape of the adjacency matrix, we'll see this structure. Right? So whereas if we permute the nodes, we see, well, quite a mess. So it's clear that there is a good amount of information in the adjacency matrix. So how we can extract that information? Let us check the expected adjacency matrix. So what would be an expected adjacency matrix even in the case of 4 nodes? Right? Just to understand the problem. So in the case of 4 nodes, we say that, and suppose we admit self-loops. That's a little bit easy for explanation. So in the case of 4 nodes, with probability P, we have a link inside a cluster, right? So it means that inside the first block, we'll have values P for all elements. The same about the second block. And we have the probability Q, which corresponds to connections across clusters. So Q will fill these 2 blocks. So we have this structure. And then we can untangle this structure in the following way. So we can write it as P plus Q divided by 2 matrix of 1 plus P minus Q divided by 2 by the following matrix. And these matrices could be written further as dyadic products. So it's P plus Q times the column of 1s times the row of 1, and P minus Q divided by 2 times the column of 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. And that's already very interesting, right? So in a sense, we have spectral decomposition, and this tells us that the first largest eigenvalue, which by the way corresponds to the expected degree, produces no useful information. Whereas the information given by the eigenvector corresponding to the second eigenvalue gives us a lot of useful information, right? In fact, in this 4x4 example, it completely correctly recovers the clustering structure, right? So if we now classify the nodes based on the sign of the second eigenvector, then we obtain our cluster. Well, now, of course, a small problem, that this is done for the adjacency matrix, right? Not the original adjacency matrix. But we can expect that this works for the original adjacency matrix, and luckily it does. So what if it works for the original matrix, what would be the algorithm? Take the adjacency matrix of the graph A, find the eigenvector x corresponding to the second largest eigenvalue of A, and assign clusters based on the sign of the elements of this second eigenvector. So why it works? It works because of Davis-Kahn-Sin theorem. And basically, this theorem says that if we have not too big difference between 2 matrices A and B, then the angle between the eigenvectors is also not large. And luckily, in our case, we could show that if we take as A our adjacency matrix and as B its expected value, then indeed we can show that this deviation is not large. Yeah, so that was one algorithm which is very popular, spectral clustering. But there are the others. So we saw that we can recover cluster structures from the second eigenvector of the adjacency matrix. But how we, in the other way, how we can find the second eigenvector of the adjacency matrix? We can find it by the following variational formulation. So we want to find the maximum of this quadratic form, x transpose AX, given the following condition. This is just the A2 normalization condition for the vector x, and this condition x transpose times the vector once equals 0 says that we're interested in the second eigenvector, not the first one, because the first one would be proportional to that. To a certain degree. So in fact, it's possible to see that that's a nice exercise. I invite you to do this nice exercise. That this formulation, if we take xi from the integer set minus 1 plus 1, becomes maximum log likelihood estimator for this problem. So we need to maximize this quadratic function under this constraint. And so how we can do this? We can, because you know, exponent is a monotone function, so maximizing the quadratic function would be the same as maximizing the exponent of this quadratic function. So in other words, we could say that we're interested to find with most likely state for the following Gibbs distribution, where the energy is given in the following form. So we put sigma transpose 1 squared as a penalty function for this constraint, x transpose 1 equals 0. And that's very interesting. It creates connection with the Ising model. So if we wouldn't have this penalty, we would have a classical Ising model on the Erdős-Rényi graph. However, now we have this connection and this penalty term, and this really helps. Because in the classical Ising model, there are 4 local minima for the energy. So plus 1 sigma plus 1 on the first cluster, minus 1 on the second cluster, or minus 1 on the first cluster and plus 1 on the second cluster. These are useful local minima, but there are 2 spurious minima. So all plus 1 and all minus 1. And these local minima actually dominant. They're deeper than the useful minima. So what this constraint does, this constraint encourages balanced magnetization, right? So the penalty is minimum when we have balanced cluster, when plus 1s cancel with minus 1. So this penalty constraint removes the spurious local minimum. So it's very useful. However, the problem, it introduces frustration. So I want to mention that here I see at least one my co-author, Daniel Sadok, from this university, and with Lucas also.
He's online. He's online.
Lucas is online. So with Daniel and Lucas, recently we finished a work about making connection between this modified Ising model and hedonic games. And why it's useful to make a connection with games? Because game theory usually provides a very natural way to distribute algorithms. So like this, we have now a distributed algorithm to make graph clustering. Okay, so that was about binary graphs, right? Graphs with binary agents. However, in many applications, we have weighted graphs. For example, in the case of connectome, the researchers measure the levels of electricity, of potential in the brain, and make and compute correlation coefficient between values of the potential. And so actually an age in the connectome has a weight which corresponds to the correlation coefficient between two locations in the brain. So you see, instead of binary graph, now we have graph with weighted ages. The same for meteorological application. So, for example, in Australia, they measure the amount of rain in various locations, and then again compute correlation coefficient between those amount of rain. Yeah, so this is actually what I said. So we now create, there are two ways. So you have a weighted graph with the correlation coefficient, say rho, of two locations, x1 and xi and xj. So there are two ways to deal with this setting. The first way, just right, so can we transform it to what we already know how to work with? So in this case, we could choose a threshold, rho bar, and if the correlation coefficient by modulus is larger than rho bar, we say that there's an age, and if rho is smaller than rho bar, there's no age. However, it's clear for everyone that we are losing information, right? So potentially, it might be better to work directly with the weighted graph. So how we can do it? We can do it actually in the framework, in a very general framework. We could consider even more general setting than weighted graph and say that between node I and j, we have interaction A coming from some general interaction space. It could be very complicated, not only real values. Yeah, so in this setting, we have again the number of nodes in the graph n, the number of clusters. So here we can have more than two clusters m. S denotes the general interaction space between nodes, and say we have now probability distribution FKL for interactions between cluster with index k and another cluster with index L. So suppose we have fairly symmetric situation where the interaction inside the cluster is given by some distribution F, and the interaction across clusters is given by some distribution G. So then we have the following result. So if we denote by d 1/2 linear divergence, which is given by the following formula, then we have the following result, which is reminiscent of the result about the graph with binary interactions. So the exact recovery of clusters is possible if linear divergence is greater than 1 plus epsilon m times log n divided by n, and is not possible in the opposite case. So just to give maybe the main idea how this type of results are proven. They are proven first looking at the local version of the problem. And so what would be the local or some researchers say Gini-aided version of the problem. So Gini discloses to us all correct labels except one. So yes, here is a black label. So we suppose we know all correct labels, but we don't know the correct labels of this node. and we would like to know what is its correct type. So we can write a maximum likelihood estimator to determine the label of this correct of this node. So it's given in the following form. I will change. Yes, and this estimator can be rewritten in the following form. So we need to estimate the probability of this event. And we do this with the help of large deviations. So in particular, the famous Kramer's theorem from the large deviations. So we use the Kramer's theorem to estimate that probability, computing all the necessary quantities of the Kramer theorem, the expectation of xi, the rate of the large deviation. And we write, okay, let me make the story short. Yes, we write this. I will. Let me mention that it's not very uncommon in random graph theory that local conditions coincide with global conditions. So right, it's the same was for connectivity in Erdős-Rényi random graph. So the connectivity of the Erdős-Rényi graph really defined by the fact that just one node is connected or not to all the other nodes. The same is true about Hamiltonicity in the random graph. So the necessary condition that you should have at least two edges adjacent to a node, right? So to create, that's a necessary condition. But it turns out that it's the condition for the Hamiltonicity in a fairly general family of random graphs. So in this case as well, right? So we just consider Gini model. So obtain necessary condition using the Gini model, but it can be shown that this necessary condition is in fact sufficient. So just to consider some examples, indeed, if f is Bernoulli distribution with parameter p, and g is Bernoulli distribution with another parameter q, then we just expand our expression for the Rényi divergence. So we use the Taylor series expansion, and we obtain what was known before for the binary graph. So we recover this result. Suppose now that we have weights which are distributed according to the normal law with the expected value 0 and the variance for the interclass connection to 1 and the variance for the cross-cluster connections to 2. So then we get this nice expression for the Rényi divergence and also a fairly easy condition for the possibility of cluster recovering for the graphs with the normal distribution, where the interaction is normal distribution.
So here the expectations can be the same. They're both 0.
Yeah, yes, they're the same. So we just we still can recover the clustering structure just looking at how it varies, how it dispersed. Quite interesting, right? So another very interesting example is an example of a temporal network. So it's what I described in the beginning of my talk. So suppose the connection between node I and J follows some on-off process, right? It's like here. So here, Bob and Alice had an interaction, but here they did not, right? And then on Wednesday, they had another interaction. So in this case, it will be on, off, on, right? So we can represent now an interaction between node I and J as a sequence on-off events. And let us model this by two-state Markov chain. So say state 1 corresponds to on, and state 2 corresponds to off. So the trick, that's what I said, the trick is to deal with the Rene divergence, right? Because it's not obvious. So in this approach, what is tricky is to get a good handle for the Rene divergence. Because here we have interaction which is represented by vectors, typically lone vectors, right? And then the Rene divergence, if you just write it bluntly, it will be in this form. So you can see here there is a lot of lone products, which is quite not manageable. So we succeeded to show that this complicated formula with many product chains can be reduced to something much simpler, which has only two terms. The first term corresponds to the sparsity of interactions. So how often we have on periods, right? So typically in the, we maybe want to consider our slot frequency based on hours, right? But maybe with our friends, we interact maybe once a week, right? So it's a very typical situation that we have sparse interactions. So we have many offs and just infrequent ons. So in this case, this term corresponds to this difference in the sparsities between the interaction. It could be even zero, right? So we could have the same frequency. So, and the second term corresponds to the difference in burstiness between the interactions. So, for example, with our family members, we could have more regular interactions, but maybe with just some acquaintances, we could have once in a while, right, interactions. But then when I visit Rio, I spend a lot of time with Daniel, right? So it's really an example of a bursty interaction. So the second term corresponds to the burstiness of interaction. So what would be the practical algorithm to deal with such a situation? So we have as our data S-valued interaction array, Xij. So in the case of temporal network, Xij is this on-off sequence, right, for each pair of nodes ij. And then we choose some set H, and that's a piece of art. And we compute the adjacency matrix, binary adjacency matrix, in the following way. If our element belongs to set J, we put 1 in the adjacency matrix, and if it doesn't belong to theta, set theta, we put 0. So like this, but again, back in business with binary interaction graphs. And we use, for example, spectral clusters. And just to give you a couple of examples, so this is the example with the where the interactions are given by normal distribution, right? And here again, we took the same 0 mean, but we took potentially different values of variance. So of course, you know, if tau is equal to 1, it's all the same, right? So there's no hope we recover the clustering structure. And indeed, we don't, right? So the accuracy 0.5 corresponds to the accuracy of a random guess. So we don't recover any, and no method can recover it, of course. However, if tau is different from 1, then our algorithm, I think it behaves significantly, right? So it's, for example, our algorithm at this value of tau gives 0.75, and the best competitor gives 0.59. So we gain significantly in comparison to competitors. Okay, and maybe I say, since I have.
Can you make a comment on theta, on big theta?
Sorry?
Can you make a comment about theta, big theta,
Yes.
in algorithm 1?
So in algorithm 1,
Yeah, set theta.
yes, so here, theta for the Markov chain, for example, it could be we do empirical estimation on P and Q, right, and set the empirical difference between estimation according to some threshold, right? So that's one way to do it.
Okay, some threshold value.
Yes, threshold value. So
From
that's
the
very
data
that's
that you
very
observe.
typical. But for example, for yes, yes, so some threshold value.
Okay.
So the same for the yes for the
Okay. And then you set a decency matrix equal to 1 based on this threshold that you decide
yes
for every pair.
yeah yes.
Okay.
So I want to, since I have a few more minutes, I want to say just a couple of words about clustering hypergraphs. So that seems to generate a lot of interest at the moment. So let's consider this very nice example. And this example I found when I was visiting a museum in Mumbai. So that's an example of women changes in Mumbai, then Bombay, and what it is. So on the perimeter, you see social activities, various social activities, all clubs. And here are the names of women influencers in Bombay. So here we say at which activity so a link corresponds, let's say, these women. I hope, or it's the other way around. I cannot even read now. So one of them corresponds to the names of the activity. Do you see? Maybe. So do you see? So what the names are this or the names are this? Can you see? I cannot read. My vision is not so good.
It's very small.
Yeah. So
We get the idea.
Oh, it's very blurry.
okay. So doesn't matter. Actually, that doesn't matter. Because you know what we need is bipartite graph. Yes. So you see. So suppose that these two ladies correspond in one activity, right? To participate in one activity. So then we say that there is an H between them. So one way is to create a graph out of hypergraph and make a clustering. But again, here you can sense that we are losing some information. So maybe it's better to deal directly with hypergraph, right? And here the graph, in this example, hypergraph is very natural. So this is the social activity, right? The social activity corresponds to a hyper H. So we have some works with the group from Aalto University, which indeed studies when you can reduce hypergraph to a graph for the sake of clustering. So, for example, in the context of hypergraphs, we managed to compute this again I. So as I said, the whole trick is to get hold of the linear divergence, right? Or information theoretic quantity for a clustering problem. So here you see it has quite a sophisticated form, right? So, and yes, I stop now. These are the references, and maybe I stop with two announcements. So the first announcement is about my fairly recent book with Maximilian Drefton. And this book has a couple of chapters about community detection, graph clustering, but not only. So it has a chapter about the introduction for random graph models, a chapter about network centrality, and also a chapter about sampling in networks. So sampling in networks is about statistical model for questionnaire in networks. And the second announcement that I have a postdoc slot in my group, and the topic of the postdoc about transfer learning and semi-supervised learning with application to fraud detection in cryptocurrency. So if some of you are interested, you're welcome to apply. And that, yeah, that's it. Your questions are also welcome.
Thank you.
Just a question. Considering that we can use this to solve problems with neurology and things that use a lot of vertex, do we
Use a lot of, sorry?
nodes vertex?
Yes, so graph could be large.
Yes.
For spectral clustering, if you use, the trick is to use, for example, Krylov-based methods for finding eigenvectors, right? So you can show that if you use Krylov-based method, the complexity could be, I think, as small as quasi-linear. So it's really applicable to large graphs.
Even if the algorithm is using matrix.
But it's sparse matrix, right? It's also sparse matrix.
Okay.
So it's typically in social networks, right? You have if I'm not mistaken, in Facebook, maybe on average you have 10 or 20 friends, right? So of course, some people could have many friends, and this is the effect of heavy tail distribution. But the average, so it means that your matrix is size billion by billion, but each row has about n non-zero elements, right? So the most important in Krylov methods is multiplication matrix by vector, right? But if you multiply sparse matrix by vector, so this makes it quasi-linear complexity.
More questions?
We can also discuss offline if you are shy.
I have a technical question.
Yeah.
So you mentioned the temporal network, like a Markov chain.
Yes.
And I was wondering if you could compute, for example, the empirical distribution of the process and use this in your previous results where you have a just FNG distribution. Could that be an approximation? So you have a temporal process.
Yes. So
but then you could kind of compute,
it's
for
very
example,
good point,
the average.
what I presented, I assume that you know parameters, right? P and Q.
Yes.
For example. Well, it's not. Especially it's needed for non-symmetric case. I think if you have two clusters and symmetric, in the same cluster you have the same connection probability across clusters, you have another connection probability. Then you maybe even don't need to know these parameters. But if the system is not symmetric, then you do need actually. It's a very good point. You need to know the parameters. So how, for example, you find P and Q for the binary graph? You compute the number of triangles, right? So one statistic would be the average degree, which P plus Q divided by 2 equals average degree. You can compute, of course, empirical average degree. So, right, that gives you one equation. And another equation would be computing triangles. So once you compute triangles, you get another equation connecting P and Q.
Okay.
Right, so this is how, for example, you can find P and Q in the binary case. In the case of Markov chain, indeed, with Maximilian and Lasse, we have an approach based on the empirical estimators of the transition probability of the Markov chains.
Oh, interesting. Very interesting. Okay, I see now more or less.
I can point you to the exact.
I was wondering how you're going to solve this. Good. Are there any questions online?
There is one.
There is one? So we have one question online coming from, I guess, Lucas. The question is, I read here, how does the structure of special cases of networks, such as directed graph or geometric graphs, influence outcomes of graph clustering?
Very good question. So, especially geometric graphs are very particular. So, in fact, I have a paper, and somebody interested, I can direct to that paper about clustering geometric graphs. It turns out that in the geometric graph, in general, you need to look deeper inside the spectrum. So for Erdős-Rényi type stochastic block model, you need to look at the second eigenvector and second eigenvalue. It turns out that in geometric graph, often the second eigenvalue and eigenvector gives you a geometric partition, right? So if you have a geometric graph and you apply standard spectral clustering, what you get geometric partition, right? So it's like, suppose we want to cluster society into men and women, right? So these are well-defined clusters. But if you make on the, say, suppose if I make here based on the proximity of the persons who see it, it's fairly mixed, right? So what we get, probably one cluster is to the left and one cluster is to the right, especially if we have the separation. So that's what gives the second eigenvector for the geometric graphs. But this is not what we want, right? We want according to the gender. So you need to look deeper inside the spectrum to find the correct cluster assignment.
Very good. Good, okay. Do you have any more questions online? No, we just have some comments. Okay. Any more questions from this side? Yeah, please.
I have a question. Sorry that I continue. But yeah, I don't know if you talked about the case with overlap. Where there is overlap.
There are works. I personally I didn't work on overlap, but of course there are works with overlap. But I didn't work on this topic. So.
Yeah, will you be interested in working on this?
In general, I'm interested in graph clustering.
Yeah.
Right, in particular, how to formulate this. Maybe, yes, it's very interesting how to deal with, say, in the context of Ising type models, right? So in the Ising type model, right? So if it overlaps, how do you deal? Interesting. Yeah. We'll discuss offline. Nice talk.
There's always more ideas to come.
Of course, there are always more questions.
Good. Any more questions to Kostya? So let's thank him again for the talk. So Kostya is going to be here for the remainder of the day.